So next I want to guide you through an example where we actually apply taint analysis to a little example program using a pushdown system. So here you can basically see essentially the same program we had earlier, only that this time we don't really care about the numeric values that are being computed or incremented here because we only want to conduct a taint analysis. So we simply assume that we have some taint here that is being propagated through these procedure calls, and essentially, eventually that is printed down here. Okay. And at the beginning, this taint is being propagated from variable t at line 1 to the same variable t at line 2. And this you can model, like I told you, through a normal rule in such a pushdown system, right? So this is saying, assuming that t holds at L1, we also know that t holds at L2. And essentially, like I said, you then have a control location here on the left-hand side. You have a stack element here, a single stack element, this line 1. And then here we essentially have a word from the stack alphabet, except that here it's only a single letter word denoting line 2 and only line 2. Then next, when this taint is being propagated here, it also needs to be propagated into the callee, right? Because t is not only tainted here, it also taints the respective formal parameter inside the inc method. And that is then actually modeled by this push rule. So this is now telling us again, assuming that L is tainted at this predecessor line, line 1, we now also know that V, the formal parameter here, is tainted at line 5. Okay. So that's done using this push rule, and it is a push rule because as an additional context, it also stores this line 2 here, right? So that is the calling context, like I explained before. So this is saying at line 5, if called from line 2, V is tainted. And like I explained, line 2 is then also the return side, right? So later on, you will see when we actually get to this return statement here, we will pop the top element of the stack, and then line 2 is the element that will remain on the stack, and that will then cause the analysis itself to continue at line 2. So this push rule, it propagates taint from T to V, and then within this callee procedure, we have a few more normal rules. So in particular, because V is tainted at line 5, V is also tainted at line 6. And because of this statement, R is also tainted at line 6. And this is modeled by these rules here. But then because R is tainted at line 6, it's also tainted at line 7, right? And so we will also have such a rule here that propagates the taint down to this return statement. Now at the return statement, let me tell you one more thing. That's actually an important note. On the left-hand side of this rule, you can see that in general, in pushdown systems, these rules, on the left-hand side, they can have statements from anywhere in the program, right? So this is a statement, line 6, that is sort of in the middle of the procedure, right? And that is generally true. So the left-hand side of such a rule, it's always the predecessor statement. It's not necessarily the first statement in the procedure. That is different from these path edges that we know from IFDS. So in IFDS, a path edge that always summarizes the entire flow from the beginning of the procedure to the current statement. But here the rule is telling us about how the flow continues from one statement to the next. And then these path edges or their equivalent, they're basically computed later through the Poststar algorithm that I will be showing you in a few minutes. Now, when we get to this return statement, we then have a pop rule, right? So we have such a rule here that tells you, assuming that R is tainted at line 7, we pop this line 7 off the stack and we taint X in this case, because X is the variable that needs to be tainted in the callers context, right? So by popping the top element off the stack, we pop line 7 off the stack, and what remains on the stack in this situation is line 2. And so we then get a configuration in which we have line 2 as the top element on the stack, and X is our control location. So basically X is being tainted at this place. And this is interesting because the pop rule, it basically doesn't know where to return to, right? If you look at the pop rule, it has no knowledge of where to return to, but it doesn't have to, right? Because that knowledge is already encoded in the stack itself. Yeah, and this then assigns the flow from R back to X here. And this is how this works in the example. Just to summarize how pushdown system rules work, so you have these normal rules that transfer state intra-procedurally from one statement to the next. And obviously you can use this for normal flow functions, but you can also use this to model call to return flow functions. Then we have push rules that model data flows at calls. And then the calling context is kept by pushing it onto the stack. And we have pop rules that model returns. So they basically pop the current callees context of the stack, and then what remains on top of the stack is the previous callers context, right? That statement, that call statement that you came from, and then the analysis will continue there. Okay, but these are the individual rules. So now what do we do with the rules? How do we actually determine reachability? And like I explained to you before, pushdown systems have this nice property that they have a computable state space that can be efficiently enumerated through this Poststar algorithm, okay? And this algorithm works as follows. It basically works by a so-called automaton saturation. So that means you always start with some initial automaton that models some initial analysis configuration. And then this automaton is saturated through a fixed point iteration according to these rules until you cannot do this any further. So just for the sake of an example, we could start with such an initial configuration that looks like this. So here we have an explicitly marked initial state, and this is now reachable from variable v at line 5. And this is basically telling us we assume that v is tainted, for instance, at line 5. Okay? And now we take a look at the rules and which of the rules we can apply in this particular situation. And you will see that this sort of left-hand side of a rule here matches these left-hand sides of these rules. And therefore, we now know that because v, L5 is reachable, also v, L6 should be reachable. And the same for r, L6. And we now encode this by saturating the automaton, which means by adding additional states or locations and edges. And you can see that this construction here already encodes that v is reachable at line 5. And now we also want to make v reachable at line 6. So it means we basically need to add another edge from v to the initial state labeled with L6. And we denote this as you can see here. But we also need to do the same for r. And r was not previously present in the graph or in the state machine, so we add it as another node. And we also make the initial state reachable from R through an edge labeled with L6 as well. Now we could also have another configuration, right? So we could also say, okay, but what if T is reachable or tainted at line 1? How does that impact the whole thing? Well, again, we could match the rule here, and now we would have to apply a push rule. And you will see that this is very similar to what we had before, only that now we have to construct two nodes, right? So we need to construct this v node that we have here, okay? And then essentially we have another node here, which is basically v at line 5, you could say, right? So it's an intermediate node. And then we still have the context information here, right? So this additional edge is now telling us that this is only valid. So the initial state here, the initial control location, is only reachable in the context of L2. And that's how we encode this context information. Or I should say the Poststar algorithm basically does this automatically when it is applied to this particular push rule in the situation. So L2, it really denotes the context here. And now again, we have this situation that we had earlier, right? V comma L5, it again matches these rules here. And again, we can saturate the automaton just like we did before. So we add an L6 edge here and R and an L6 edge there. And now you can see that this situation here, it again matches this left-hand side rule that of the rule that you see here. So now we can actually apply this particular pop rule here. Okay. And this is what you get here. So by applying a pop rule, we basically pop this particular context off, you could say. So this, we follow this edge, which brings us here. Okay, so that's like popping this off the stack. And then we see that the initial state here, or the next state, is reachable through L2. And so we create a new state for X, because we don't have a state for X yet. And we connect it to the same state here also with L2, right? So this is basically saying that this state and this state, they are equivalent, except for the label that we have here, right? Except for the tainted variable, they are equivalent. And we want to have this, right? Because that's basically the effect that we want to have by popping off the current context of the stack and continuing at this particular location here. And yeah, this is basically how this worked in this simple example. And now I next want to show to you in a bit more detail how to actually read these Poststar automata, right? So let's take another look at this slightly extended example here that actually has also a recursive call. So here at line 2, we are tainting some value R, which is propagated to S, which propagates into foo, where it is called T. And then we may have such a recursive call, or we may just return. And then in the end, the tainted returned value is also assigned to U. Okay? And now if you look at the data flows, it basically looks like this, right? So obviously R is tainted all the way here, but we are also tainting S. And then at line 4, at this call, this S is being assigned to T. And T also flows here to line 8, where it may be again assigned to itself, right? That's by the recursive call. But T also flows all the way to the return statement, where we then return. And here, yeah, you will see later why these labels are important. They are important because of the rules. Okay. So in this example, we have, again, normal push and pop rules, right? So we have the normal rules for the intra-procedural flows, basically the grayish edges that you see here. But we also have these push rules, right? So S at statement 3 is being assigned to T at statement 4. Sorry, at statement 6 in the context of line 4, what you see here, right? But we also have the situation that T from line 7 is being assigned to T at line 6 in the context of statement 8, right? This is the recursive call that you see down here. And we have pop rules, right? So we have return flows. So here, for instance, we have a pop rule that is assigning T from line 9 here to a variable u up here. And actually, this is not quite sufficient. We're actually missing a pop rule here. I'm just noticing you would actually also have a pop rule from t at line 9 to t itself, because we could also be returning to this location here, right, when we have a recursive call. So basically, you need different pop rules for different call sites. I'll get back to that in a few minutes, actually, but this is also relevant here, right, because this is tainting u at the place at which you return, but you actually want to return, you also want to taint or continue to taint the return value here when you actually return from this recursive call. That's actually important. So when you implement this in a static analysis framework, you need to take care that you have these differing pop rules at the different calling contexts. Now, again, if you do this Poststar construction, this construction of the Poststar automaton, this is what you will get. And now I briefly want to explain to you how to actually read off the different values of this automaton. Now, let's take a look at these different statements here. So we have the call to foo, which then goes to line 6, but then also we have the recursive call to foo down here, right? And so this means the tainted value, it could flow all the way here, through statement 4, through statement 6, through statement 8, maybe again through state 6, and so on, right? And you can basically see this by following the edges that you see here in a backward manner, right? So initially we have a tainted value here, right? And so for instance, R at line 2 or line 3 or line 4 is holding this particular tainted value. But then also, because of the call at line 4, and potentially through recursive calls at line 8, we have the situation that T at line 6 and 7 and 8 and 9 will also hold this tainted value. And so you basically have a reachable configuration here that you can read as, depending on in which direction you read it, 4 a number of times, 8, and then 6, right? And then also, because of all of this, and because the return value actually flows into u, u is also tainted at line 4. Okay, that's this greenish part that you see here that basically relates to the left-hand side of that statement. That's how you can read off these solutions, right? So this is basically telling you R is tainted at lines 2 or 3 or 4. This is telling you U is tainted at line 4. And this is basically telling you T carries some value at line 6, 7, 8, and 9, which propagates through recursive calls at line 8. And then in combination with this edge here, you also know that this value is actually tainted at line 4. And you will see now that this Poststar automaton, it might be a little complicated to read for us human beings if you are not used to this, right? But it's actually a very neat and concise encoding of the entire analysis state, right? So we not only know which information is tainted at which program locations by just reading it off the automaton, we can even model context information, and we can even model recursive calls and recursive cycles in this context information. And that is really all that we need, right? So to summarize this Poststar algorithm, Poststar computes the configurations that are reachable in a pushdown system. And there's actually a theorem that proves that if you have regular starting configurations, so basically a starting configuration that can be described by a regular language or a finite state machine, then the Poststar algorithm saturates that finite state machine using these pushdown systems rules such that the output is also guaranteed to be a regular language or a finite state machine. So the algorithm essentially applies rules in one large fixed point computation, and the result is then essentially a finite state machine describing a regular language. And in our model, these states then represent variables or also access paths in the more general sense. And the transitions, the state transitions, they encode at which statements and in the context of which other statements, so in the context of which calls, these access paths hold or are tainted in the most simple scenario. That's all I wanted to tell you about Poststar. In the next video, I will explain to you how pushdown systems actually work with summaries. And as you will see, they actually incorporate summaries automatically, which is also a very nice property.